There's been few things that somebody has dreamt up in human history that rival this. As the media calls it, the God particle. I talk about the serving sizes on the Nerd's Candy too. You didn't have to be a nerd to figure out with Jim Smechlin. We're going to be looking at a song called Beat of the Sun. Okay, so Einstein, his whole theorem, where it all came from, it's not E equals mc squared. That's just pop culture crap.
What?
His brilliance was special relativity. He came up with this idea of special relativity. It changed the world. It still, to this day, you hear the things that they're doing with quantum mechanics and these particle accelerators and things. What Einstein came up with in special relativity doesn't fit with the current model that they're working on. Now he called it a Gedunken, a thought experiment. So this is essentially a guy sitting around looking at the facts, looking at actually one very simple fact and saying, oh, well, if that's true, then the universe is something completely different than what we think it is. It's quite amazing. This is like the brainstorm of the century. This is the brainstorm of mankind. The first premise, the fact that he was working on, Armand Hippolyte Louis Fizeau and Jean-Bernard Léon Foucault. This is, I don't know my history well enough. I should have looked. This is another thing. Sometimes I should look things up on the show before I start talking about them. They set up on one side of a hill. They had a spinning machine, and depending on the speed that they were spinning this thing with the mirror, they could tell the duration it took for a beam to go there and to come back. If this is spinning at a certain rate, you would be able to get the bounce back and see it. Anyway, they determined that the speed of light was a constant. Because here's the thing, they do this experiment, they go one side hill to another. Amazing, okay, we got the speed of light. Now say, one of them had the bright idea, well let's reverse it. Let's put the register in here and the spinner here to test the theory that it would be different depending on which way you're going in relation to the spin of the planet. So the planet's spinning this way, we fire a beam with it and back, and then planet spinning this way, fire with it and back. Planet spinning with, maybe go sideways against the grain of where it's spinning, see if you can get different results. And what they found was in every experiment that they tried to get the speed of light, they got the exact same result. It didn't matter which way you were pointed in regard to the spinning of the planet, you always got the same result. If I'm in a car and I throw a baseball and the car's driving, well the baseball is going to lead my hand at whatever speed I can throw plus the speed of the car. And you would think that that light would work the same way, but it doesn't. Well, Einstein said, Einstein pondering that thought, yeah, speed of light is constant in every direction, came up with this special relativity, and it's what everything else that he came up with was based off of this one amazing idea. Let's imagine we're standing here on the planet and there's a train, okay? There's going to be a train flying past the planet Earth at a speed that's almost as fast as the speed of light, okay? Now within the train, there's a train car, and within the train car, here's the train car, there's a light at the bottom and a mirror on the top of the train car. So they fire the light, and he watches it go to the top of the train, he watches it go back down. So he records, obviously speed of light is a constant, so he sees that it takes the amount of time it should take for light to move from one top of the train car to the bottom. Now us, sitting here on planet Earth, watch him do that experiment as he's passing us at near speed of light. He's going incredibly fast. So train is moving. For us, the train is moving. Train is moving. Here, he hits the laser, and laser moves up. But wait, the train car keeps moving. It hits the top, and it comes back down, right? So as the train is moving, he's sending the laser up, but it's going to do this kind of pattern, right? Because the train car is moving. So, and we get the same result. We're watching the same experiment. We say, okay, speed of light is a constant, but when he looks at the experiment, he sees the light moving this distance, right? When we see the light moving, we see the light moving this distance. we watch the same experiment, so we know that light is moving at the same speed, but somehow we see the exact same light covering a much greater distance than he sees it covering. Time and speed multiplied equal the distance. If you change the numbers, the equation still has to make sense. And so the speed of light is constant. We know that one's not changing. But distance is changing. So if the distance is different for him than it is for us, the other variable must change as well. The time variable itself has to change. There's more distance there, and if there's more distance, more time must have passed. That's how you got more time into your equation, is because time was actually moving slower in your position than it was for us. You know, we're watching you, time's moving slower for you. It's the only way that the equation can make sense. Let's look at the headlights of the train for a minute. Let's say that the train flips on his headlights. Now the guy sitting in the train, he flips them on, he sees it move away from the train at, you know, normal. He's in his reference frame, he's absolutely still. It's the same way that we're moving on this planet. We're moving very quickly while we're on this planet, but to us it's still. He's in this train, to us it's moving very quick, but to him it's perfectly still. He flips on the lights and he watches it shoot away from the train at normal speed. Now us, sitting here, watch the same experiment. We see him driving by with a train, he flips on the lights, and we see the distance that the light shoots out of his train at the constant speed of light, but we also see the movement of the train. We end up seeing a much, much greater distance. We're seeing the headlights go further. Now the only thing that can give in this system is space itself. The only way that this can make sense is if space is crunched up for him from our point of view. More compact for things that are moving faster. And that includes the guy on the train, that includes the train itself. So the train may be this big, but there is actually more space, more of this stuff that we're moving around in, this universal space, is crammed down into the train, which also makes the train itself more dense, because if there's more space in it, that means technically it's bigger. If you took the whole universe and crammed it down into a baseball, that baseball would then be the size of the universe. Space actually crunches up and becomes more dense for something moving quick in relation to us. And these principles, amazingly enough, have been proven. They sound absolutely crazy and ridiculous, but they've been proven. If you take two clocks and you put one at the top of a building and one at the bottom of a building, and you let them go, they will go out of sync. The one at the top will move slower than the one at the bottom, because remember the planet is spinning, right? So if you have a spin like this, these parts of the spin further out are moving faster than parts in here. You can see, as this is spinning, the outer edges of the spin move much, much quicker. So the top of a building moves faster than the bottom of a building. Something would become more dense, something would become a bigger mass if it's moving fast in relation to us. And if you look at something that has a bigger mass, like a sun or a massive planet, light waves actually bend when they go past a sun. You can look at stars that are behind a sun. Light waves bend when they come close to something with lots of gravity, because space itself got crunched up. And when it's like when light hits a piece of glass, like a dense piece of glass, it changes direction because it's hitting something that has a different character. And space itself bunches up when something's moving really quick or when there's a really dense mass. And this is where special relativity hits quantum mechanics and says that it doesn't make sense, because Einstein's theory says that, as something gets more and more space crunched into it, the faster it goes. If it were theoretically ever to reach the actual speed of light, a physical piece of matter were to reach the speed of light in relation to us, its density would be infinite. So it's impossible, because you can't have infinite density. The physical universe, adding some science to the show. I hope some or any of that made sense.
News fail.
News fail. So this time on the news fail, I want to talk about this as the media calls it, the God particle. It's just another physical thing that they've found in the world. And it's got a lot of bizarre principles. It's one of these things that they say can sit over top of each other. So you could have multiple Higgs boson particles on top of each other in the same location, which seems crazy, but one of the things coming out of quantum mechanics is that, you know, maybe there's multiple world theories, that there are in fact other universes sitting right on top of us all the time, and that, you know, we can't see them, we can't transfer back and forth, but that there are particles that can switch back and forth between the two, and that would explain some of the weird things that come out of quantum mechanics. The particle accelerators, these are these giant devices. They bring something, a massive area, and they spin it around really quickly, and then they collide, and these weird particles shoot off. It's also what the Ghostbusters wore on their backs. Hollywood culture phenomenon that has nothing to do with the actual term. This labeling of the Higgs boson as the God particle, this is to further divide science and religion. Because, you know, to glance at it, if you're religious, you're going to glance at this, you're going to say, oh, those damn scientists, they think they found God. And the scientists aren't actually saying that. They don't even want this. They don't want to call it a God particle because it's just another particle. I mean, it's like when somebody found the atom. Atom means indestructible, smallest thing. Yeah, right, we found all kinds of things that are smaller than atoms now. Just a particle, and those are its characteristics, and that's how it interacts with the world. If you're religious and you're anti-science or something, I mean, get on board. Science is about the study of God's majesty. There's nothing blasphemous about it. And scientific people, if you know you like to say things that, oh, this religion is crazy, well, metaphysics are always going to be out of reach of science. I don't care how far you go, there's always going to be the possibility that there's a God behind things. Consume! Hey, consume! I got Nerds Candy. Got some Nerds Candy. It's a science episode. Thought that'd be good. It's got the Wonka, because, you know, it's, you know, something that a lot of us remember from our childhood, the Wonka movie. Sure, now it's just marketing. Make you eat chunks of fluorescent chemicals bunched with sugar. Oh, I was going to have a wand. I was going to have a magic wand. Wouldn't that be nice? I could do, and then there would be, you know, maybe I'll just fake it. Have a magic wand, and we'll have the Nerds Candy here, but of course one time we're going to flip it and it's going to be a box of some sort of toxic barrel or something there. I think that'll make a good image. And serving size. I just want to talk about the serving sizes on the Nerds Candy too. You'd have to be a nerd to figure out this. A kid couldn't figure this out. The serving size is 15 grams, and the box size is 46.7 grams. So there's 3 and a tiny bit servings in here, and of course it's divided into 2 as well. So it's a sixth. It's a little less than a sixth of each side that you should eat in a serving. I think if my math is a third. I don't know. I can't even figure it out. This is too confusing. Why don't they just make serving sizes standard so that you know what you're getting? You can look at the nutritional content and it would actually mean something. Little Johnny, he's a brilliant kid. He's packing his face with these fluorescent sugar balls of chemicals. Ooh, my little Johnny, he's brilliant. He figured it out. He knows how much the serving sizes are. Culture with Mr. Jim Smetchland. This week on the show, something scientific. Going to cover a song by Remi Stevens, in part done here at the studio, I think. The drums were done here. This song is called Beat of the Sun. It's about frequencies of light rays, how there could be a beat to that, potentially. If you could drum that fast, there would be a beat. Tens of thousands of beats per second. Okay, Beat of the Sun. I'm Jim Smetchland, and this was the Remi Review.
cha cha.